All right, let's get started. I again put up a review of yesterday's lecture because we introduced lots of new concepts. We went through the Hecke algebra abstract construction as a Z module of formal finite linear combinations of right gamma and cosets. We were able to define a product, and lots of nice properties were at least listed out. Some of them you were trying to figure out in exercises. So Hn can be decomposed into these Hnp's for every prime p, and for every prime p we have very nice n plus 1 generators. After this abstract business is done, we can hit these Hecke algebras on modular forms, and once again in the exercises we check that indeed what you get is a modular form, and you have this slash action which makes everything work. These Hecke operators is a big family of commuting self-adjoint operators, and so you can diagonalize the space of modular forms and you can start talking about common eigenfunctions. And from these Hecke eigenvalues of these common eigenfunctions, we were able to write down these for every prime p, these n plus 1 numbers which were the Satake p parameters, and they then very naturally gave rise to the definition of two L functions. The spin L function is the degree 2 to the n L function. It's a rather huge one as n becomes bigger, and we know very little about the properties. We were saying only for n equals 1 and n equals 2 we know meromorphic continuation, location of poles and functional equation. N equals 3 is very recent, and n equals 4 and beyond is nothing is known. On the other hand, the standard L function is much smaller in the sense that the degree is 2n plus 1, so it's just linear in n, and in this case, so the formula is also much simpler, and in this case indeed all the nice analytic properties are well known for all n, and in fact I mean many of the things that we are doing here, or rather all the things that we've been doing here are for gamma n. Similar definitions and similar concepts can be also introduced for Siegel modular forms with level and for congruent subgroups, and for that also a lot of things are known. So maybe from time to time I'll mention these things, but we are concentrating mostly on gamma n. So what I want to start with today is writing down the L function of a Saito-Kurokawa lift. So how does it look like? Saito-Kurokawa lift can be obtained from a modular form of gamma 1 to modular form of gamma 2. Is there a relation between their L functions? Okay, so let me just remind you, Saito-Kurokawa lift, we start with f S2k minus 2 gamma 1, and I am assuming it's a Hecke eigenform, and also k is even. And so the Saito-Kurokawa lift is a Siegel modular form f sub f, which is cuspidal, weight k, and gamma 2. So during the discussion in the afternoon yesterday, I suggested those who were present to try to see if you can find a relation between the Hecke eigenvalues, Tp Hecke eigenvalues of f sub f out of the p Hecke eigenvalues of the. Did you guys get a chance to think about that? It was quite complicated.
I took that matrix is this P 0 P that diagonal matrix. But in that case, I didn't get anything special.
Oh, okay, okay. So maybe we can look at it again briefly today afternoon to see what happens. And in fact, you can have the Hecke eigenvalues here, even though in the genus 2 case, the P Hecke algebra is generated by 3 Hecke operators, right? Tp and those two guys. One of the 3 is just the identity operator, so in fact it just ends up being Tp and T of p squared. So Tp and Tp squared, this generates the Hecke algebra at so H2p. And in general these are algebraically independent, so the Hecke eigenvalue should have no relation amongst them. But just because you come from a elliptic modular form here, in fact these two guys are related. That's what turns out in this Saito-Kurokawa case, and in fact what you get is where this LSF is summation a n over n to the s, n equals 1 to infinity, and the a n's are the Fourier coefficients of f. So, the L function factors into a product of L functions of smaller degree. So, zeta function is degree 1. So, you get a shift of the zeta function, 2 of them appear right here, and the L function of the input. So, this is something quite nice and explicit relation between the L function of the Saito Kurokawa lift and its input, and this is a pure, this is not ever going to happen for Siegel modular forms which are not lifts. And in a certain sense, the philosophy is that if you have a cuspidal object whose L function factors, then it has to be some kind of a lift. So, in this case, indeed this is what is going on. You can see already that if you remember, the Riemann zeta function has a pole at s equals 1, which means this guy has a pole at s equals k. If you remember, Andrianov had proved that spin L function of a general cusp form of genus 2 has at most simple pole at s equals k minus 2 and k. These guys do have poles. In fact, it is not that these guys do have poles. It was proven by Oda and Evdokimov that this existence of a pole actually characterizes being a Saito Kurokawa lift. What do I mean by that? If you take any arbitrary Siegel cusp form of genus 2, you do not know anything about Fourier coefficients, you do not know anything about recurrence relations, nothing, but you know that the L function has a pole at s equals k, implies it has to be a Saito Kurokawa lift. So, that is a brand new completely different characterization of something being a Saito Kurokawa lift. So, this has a pole at s equals k, and only these guys do. So, that is the result coming out of this guy. Of course, as soon as this factorization of L function happens, we know already that the Riemann zeta function has some kind of functional equation among within itself. So, if you take the zeta function and you multiply it by gamma s over 2 and pi to the minus s by 2, then the resulting function satisfies value at s is the same as value at 1 minus s. So, both of these guys satisfy certain functional equation. This thing here, a modular form of genus 1, also satisfies a functional equation with s goes to weight minus s. So, one of the first exercise that you have is take the functional equation that you get from this guy and this guy and this guy and derive Andrianov's functional equation for this one. How do they all combine together to give exactly the thing that is there in the theorem we wrote down yesterday. So, that is a very instructive exercise in how things happen here, and it is a nice one. You will, I hope, rather enjoy it. Another thing that you can do is, if the spin L function looks like this, what about the standard L function? So, as soon as you write this, you should be able to figure out everything is a product over all primes, right, the way it is defined. So, as soon as you write like this, you should be able to recognize what is alpha 0, alpha 1, alpha 2 here. Okay. We will look at that alpha 0, alpha 1, alpha 2 again in just a few minutes, but as soon as you have your alpha 0, alpha 1, alpha 2, you can write down the standard L function, the degree 5 L function. And in fact, what happens in this case is the degree 5 L function also factors, and it factors slightly differently. You have a zeta of s and you have s plus k minus 1 of little f and s plus k minus 2 of little f. And this I am going to leave as an exercise, and again I just told you exactly how the exercise should go. Find out the alpha 0, alpha 1, alpha 2 and then write it down and recognize what is going on right here. If you have a lift, the L functions are factoring, and that is kind of following a very nice general principle as well. Okay. So, now what I want to do is I want to tell you about one of the most important things in life, generalized Ramanujan conjecture. I know Ramanujan did a million things and they were all remarkable, but at least in my limited experience, this is the depth of Ramanujan conjectures is unparalleled actually, and their applications and their scope. So, I am writing generalized because usually the Ramanujan conjecture that you see is for genus 1, and now we are going to generalize it, and let us see what it says. So, suppose F is genus n, now we are back to genus n, and I want this to be a Hecke eigenform. So, usually for genus 1, when you write down Ramanujan conjecture, you write down some estimates for Fourier coefficients. So, actually those estimates for Fourier coefficients can be translated into estimates for Hecke eigenvalues. Those estimates for Hecke eigenvalues can be translated into estimates for the Sataki parameters. So, the way we are going to state this is in terms of the Sataki parameters. So, it might look unfamiliar in comparison to what you know for these guys, but there is a jump: Fourier coefficient, eigenvalues, Sataki parameters, and all of those statements are equivalent. So, suppose we have such a guy, and alpha 0 p to alpha n p are the Sataki p parameters. So, it is about what kind of estimates these satisfy. So, in general, with very little effort, you can show that for all modular forms, these conditions are always satisfied for all I. These are what are called as unitary estimates. The easiest way to see this actually is going to the representation theory side of it, and then you say that, well, the representation you got is unitary, which means some characters have to have absolute value 1, which spits out a relation like this. So, this is easy unitary estimates, and the Ramanujan conjecture says that no, I do not really have any freedom, these guys have to be 1. Okay? So, I should actually say I p and I equals 1 to n, not the alpha 0, I am only including alpha 1 to alpha n. So, generalized Ramanujan conjecture we will denote it by GRC. So, GRC states and for example, you can imagine now one of your exercises yesterday was that the Hecke eigenvalue lambda of p was p to the k minus 3 by 2 alpha plus alpha inverse plus beta inverse. The alpha, beta, etc. are exactly these guys. So, if these guys have some kind of estimate, you can translate to an estimate for lambda p. So, that is what I meant. Even though I am writing it down in terms of Sataki parameters, this can be translated to the Hecke eigenvalues, and in the higher genus case, going to Fourier coefficients is much harder. So, you just look at Hecke eigenvalues. So, of course, the hope is that this is true, because indeed it has been shown to be true for genus 1. So, Deligne's theorem is true for f in S k gamma 0 n chi. So, I am throwing in a chi as well, we have not really mentioned this. So, any genus 1 cusp form of weight k, level n, and Nebentipus chi. If you do not know what Nebentipus is, it is fine. It is the most general kind of holomorphic cusp form. So, this is a theorem of Deligne in the 70s. It would be nice if it was a theorem for general genus, but already no, it is not. I mean, that is the whole point of this Saito Kurokawa business. Saito and Kurokawa constructed concrete examples of genus 2 Siegel modular forms which violated this guy, equal to p to the half. They got the extreme ones, and we will see exactly why that is going on here. Counter examples in genus 2. So, basically suppose, so we are going back to the Saito Kurokawa situation. So, Saito Kurokawa lift. So, my f is in S 2k minus 2 gamma 1. Before I go here, let me just mention that once again in your exercises, you had shown this relation here, alpha 0 squared alpha 1 to alpha n is p to the k n minus n plus 1 by 2. You showed this for n equals 2 in your exercises. This was the coefficient of x to the 4, if you remember. If now you say the Ramanujan conjecture says that each one of these is equal to 1, in fact I am also making a statement of alpha 0, because alpha 0 you can, the absolute value of alpha 0 you can glean out from this thing. So, do not think that we abandon alpha 0 here, it is kind of automatic from that relation. So, start with f, and f is going to have, I am going to call these beta 0 p and beta 1 p, okay, two Sataki parameters. Of course, beta 0 squared. So, if all of these are 1, beta, so I am replacing my alpha 0 by beta 0, beta 0 squared is p to the k minus 3, right? No, n is equal to 1 here, n is equal to 1, so no, not 3 then, k minus 1, p to the k minus 1
divided by 2.
Yes. So, okay. So, let me write down the answer and then we can k minus 3 by 2. So, indeed alpha 0, this is p to the k n by 2 minus n plus 1 by 4. And the reason I got k minus 3 by 2 there is because my weight is 2k minus 2, by the way. That is the reason I do not see k times 1 by 2, I actually see a k there. So, that is the thing that you have to remember, the weight here is 2k minus 2, and of course, beta 1 p has absolute value 1. So, now if you look at your spin L function, then at every prime p, what are the roots of the factor? So, for every prime p, I got alpha 0 p, alpha 0 p, alpha 1 p, you know, I am going to just suppress the p here, alpha 0 alpha 1, alpha 0 alpha 2, alpha 0 alpha 1 alpha 2 has got to be LSF is going to give me beta 0 and beta 0 beta 1, and a zeta is going to give me p to the k minus 1 and p to the k minus 2. So, this guy is exactly 1 over 1 minus p to the minus s times t p to the k minus 2. So, this is my coefficient of p to the minus s. So, this is my p to the k minus 2, and the first one gives me p to the k minus 1. So, now if you stare at this long enough, you will see that because of the p to the k minus 1 and p to the k minus 2, so you should think of it this way. This is p to the k minus 3 by 2 plus a half, p to the k minus 3 by 2 minus a half. This has absolute value p to the k minus 3 by 2 and p to the k minus 3 by 2. And so, what is going to happen is alpha 0 you expect to have absolute value k minus 3 by 2, and so alpha 1 alpha 2 ends up getting p to the half and p to the minus half. This implies have absolute value p to the half or p to the minus half, contradicting GRC. It will require a little bit of a thinking, but the main idea is that the p to the k minus 3 by 2 is what alpha 0 gets you. You try to divide one by the other, and what you get is what we are looking at. So, there are counter examples. So, is GRC to be thrown out of the picture? Well, no. Apparently, for genus 2, gamma 2, so full level, if you are not a Saito-Kurokawa lift, there is a theorem which says that it actually satisfies GRC. So, that was a big thing. So, theorem due to IISER. This was ultimately published in 2009. This says that if f in SK gamma 2 is not a Saito-Kurokawa lift, then f satisfies GRC. So, IISER claimed to have proved this already in the 90s, and then he wrote it all down and put it on his website and never submitted it. And this was the biggest disservice that he did, because if you are writing a paper, can you use it? If it is not, I mean, I can write a proof of Riemann hypothesis and put it on my website, right? Of course, nobody will believe me, but maybe some big shot could do it. But you can't use it. You can't use somebody's personal notes as a basis of your further theorems. So ultimately, so Winfried Koenen was telling me that they made Weishauer write this into a lecture notes and it's published. And then I was asking Koenen, did somebody really referee it? He said, yeah, of course. And that okay. So Koenen's seal of approval is there, and so this is a theorem for sure. Now we can safely quote it. I mean, since 2009. So in fact, when I finished my PhD in 2006, and I went for my postdoc, and first few papers that I wrote were related to some Ramanujan kind of results, and this I exactly faced this difficulty. Well, do I use Weishauer or not? We decided to avoid it, but now you can use it. Okay, so theorem, this is genus 2. How about genus n? Now genus n story is, at this point it's open, but there's a good chance that a genus n generalized Ramanujan conjecture might be within reach, and it's within reach possibly using really high powered machinery. Me and my collaborator Ralph Schmidt, we were thinking that now Arthur has this transfer from GSP2n to GL2n plus 1, could we use that? And then the pieces are that you go from GSP2n, a Siegel modular form of genus n, you transfer it to GL2n plus 1, and for GLN Ramanujan conjecture is not known in general, but it's known for a certain subset, self-dual and some properties satisfied at the Archimedean place, which depends on the holomorphic, etc. It seems that when you transfer, all the nice properties are satisfied, and the lift that you get is indeed satisfying GRC. So all these things, dots have to be connected, and maybe if we have enough motivation, me and Ralph will do it, or maybe somebody else will do it before that. But it looks like enough smart people have proven big theorems that now this is just connecting dots for genus n. Of course, the difficulty is it's not going to be true for all Siegel modular forms. What is the equivalent Saito Kurokawa lift, guys, that we have to avoid for general genus n? And that's a very serious and complicated question. So we'll have to see which Siegel modular forms, when you transfer to GL2n plus 1, give you a Cuss form. And I know for many of you these words are not making sense right now, but when you take a Saito Kurokawa lift, it transfers to GL4, but it gives you an Eisenstein series. So it does not give you a Cuss form, and so it does, the violation of Ramanujan is not some serious breakdown of beliefs and whatever. But the story of GRC is actually only written down and complete only up to genus 2, and already there are quite a few amazing applications that come out. So in the course of lectures, I am going to give you several applications. I want to mention one of them right now, and then later we will have occasion to look at many more. And
why do you write F belongs to SK gamma 2?
I am starting with a Cuss form, and what I am saying is maybe when I transfer it to GL, I don't know if it is cuspidal or not. So Cuss forms could transfer to non-cuspidal stuff. And that's exactly what happens to this guy. You get a residual on the other side. Okay, application, the application is going to be super impressive, okay. So this thing is a big short theorem, and it gives you really crazy stuff. So let me tell you the application. So this was a work that I did with Ralph Schmidt, David Farmer, and Nathan Ryan, yes.
There are also those other families of like automorphic representations of this which don't satisfy GRC, right? Or maybe they're not expected to. Like,
for GSP4, you mean?
yeah, wasn't this?
Yes, that's right. So there are cap representations coming from the Borel or the Klingen, but then there is a theorem you can prove that if you're looking at gamma 2, the only exceptional things that can occur are Saito Kurokawa types. If you start to do level, then there are others. Yeah, absolutely right. So when you look at not gamma 2, but other congruent subgroups, then you have to avoid, if you want to write down a theorem like this, because Weishauer's theorem is not just about gamma 2. It's about all Cuss forms of any level and any Nebentypus, as long as they are not cap. So this is cuspidal associated to parabolic, or in other words, it's L functions factors or something. So some equivalent ways to look at it. But for genus 2, I can actually write down exactly what the exceptions are. Genus 2, gamma 2. I can write down exactly the exceptions, and that's the theorem there. So, what is the application? Okay, so the application is the following. I really like this stuff. So, Fj for j equals 1 to 2 are in S kj gamma 2. These are Hecke eigenforms with eigenvalues lambda j of n. Okay. So, in general we talked right here that in the genus 2 case, for every prime p you have two algebraically independent Hecke operators. So, lambda p and lambda of p squared should have no relation. You should not be able to find a formula for one in terms of the other. Okay. That is the meaning of being algebraically independent. But now what I am going to write down is the following. If p to the 3 by 2 minus k1 lambda 1 p equals p to the 3 by 2 minus k2 lambda 2 p for all but finitely many primes, p, then k1 equals k2 and f1 and f2 have the same eigenvalues for all Tm. So, lambda 1 m equals lambda 2 m for all m. So, if you knew that lambda 1 p equals lambda 2 p and lambda 1 p squared equals lambda 2 p squared, then you could say lambda 1 p to the r is the same as lambda 2 p to the r, because these generate. Once you get powers of prime, you could multiply and you get all m. But only one guy, so these powers of p are just to normalize it, but only one guy giving you the whole thing is somehow telling you that is there some mistake with the algebraic independence? Absolutely not. So, somehow this theorem you should realize is a big surprise, because the reason I am saying it is a big surprise is, even though I am claiming that this is actually equal to true, you ask me, oh, can you tell me what is the formula for lambda p squared in terms of lambda p? It seems that it does not depend, it is not an independent thing. I can't give you a formula, but I can tell you that they are equal, and this is somehow coming from the fact that these guys satisfy Ramanujan, and because they satisfy Ramanujan, you can actually do a very interesting analytic number theory argument. Basically, you look at the spin L function of f1 and the spin L function of f2, and you write it as a Dirichlet series. You define it as an Euler product, but you then multiply everything out and write it as a series, and the pth coefficient of the series are exactly these lambda p's. So, I am claiming that if in general I have two Dirichlet series summation a n over n to the s and summation b n over n to the s, where the a n's and b n's satisfy certain estimates, and those estimates I am going to get for these guys from the Ramanujan. Okay, that is where the Ramanujan comes in. Dirichlet series with coefficients satisfying some nice estimates, it is enough to just check that their pth coefficients are the same. You can put some very not very sophisticated, but apparently standard analytic number theory techniques to show that there is a multiplicity 1 of L functions. The L functions or the Dirichlet series match up, and as soon as the L functions match up, that is the definition of the Hecke eigenvalue matching up. So, Ramanujan really gives you extremely surprising things. Those of you who know about the representation theory, if you look at the automorphic representation and the local representation at prime p, you know that it is at the spherical ones, it is given by these Sataki parameters, the diagonal. What you are saying is that if the trace is the same, the lambda p is the sum of these Sataki parameters. If the trace of these two matrices are the same, the representations have to be the same. So, it is quite surprising, and apparently analytic number theories knew this. So, whenever I talk about this to an analytic number theory person, he says, oh yeah, automorphic people, there is a mistake here. So, apparently not. Okay, so this is a very nice application. We will look at a few more as we go along.
Whose theorem?
Whose theorem is this? Farmer, David Farmer, Nathan Ryan, myself and Ralph. Yeah, the analytic number theorists are David Farmer and Nathan Ryan. I got to learn a lot of this stuff, writing papers in topics outside my comfort zone. So it's a good thing. Any questions?
So here F1, F2 are SK lift?
No, nothing. No, not lifts, because I am assuming Ramanujan, right? Good point. So let us just assume that they are not Saito Kurokawa to make our life easier. Okay. If they are both Saito Kurokawa, then it's even easier actually, because it just even easier actually, because it just
This one, this is two.
no, the fact that both Tp and Tp squared eigenvalues can be written in terms of eigenvalue of the F. So if you knew Tp, you essentially knew Tp squared. So that is the reason why for Saito Kurokawa it's not a surprise, but the fact that it's also true for arbitrary cusp form is the power of Ramanujan.
Here, can we write lambda p to the power r in terms of lambda p and lambda p squared?
Lambda p to the r in terms of lambda p and p squared. Theoretically, yes. Ask me a formula, I have no idea. You will have to figure out the relations in the local p Hecke algebra of Tp, Tp squared and so on, what kind of things. And that's perhaps just look at those double cosets and see how it happens. So it's not, yeah.
So Smith theorem can be can be strongly, one can say strongly, like here in the hypothesis he assumed that lambda p to the power r, lambda 1 p to the power r is lambda 2 p to the power r for all r greater than or equal to.
That's right.
So we can generally say for r equal to
1 and 2, you are absolutely right. In fact, it's a good thing that you suggested Schmidt's theorem. What he's referring to is the theorem that we said if two Siegel modular forms have the same Hecke eigenvalues, you don't expect to be the same because Fourier coefficients are complicated, but they were indeed the same. And now you see you don't even need r equals 1 and 2, only r equals 1 works. So that's, I think, one of the easiest exercises that you have today. Just say the word Schmidt's theorem and this theorem and the answer comes out. Basically the exercise is if the two guys have the same p Hecke eigenvalues, then they are multiples of each other. I just wanted you to make a connection, but you already did. So
one small question, why do we call it spin? The word.
The spin L function, yeah. The reason is a little complicated, and this goes back to how you would really define L functions. And the formal definition of L functions actually is a recipe of Langland's. And I'm going to say some words now which many of you might not understand, and it's okay if you don't. So if you have GSP 2n, then there is something called as an L group associated to it. In this case, it's G spin 2n plus 1 of C, complex numbers. Here GSP 2n could be rationals, reals, adels or something, but the L group is always a complex group. And then corresponding to linear transformations of this group into various GLMs, you can define an L function for each one of these linear transformations. The degree 2n plus 1 comes out of the standard embedding G spin 2n plus 1 is just 2n plus 1 by 2n plus 1 matrices. So it's contained in GL 2n plus 1. That gives you the standard L function. Where is the standard? Okay, up there. And the spin comes from a much more complicated spin representation which goes to GL 2 to the n. So every such transformation into different GLs gives you a definition of a new L function. In this case, so that's the reason for the name, I think. I think when Andrianov or Maas were doing this, they never called it spin L function to begin with. They just did summation of the Hecke eigenvalues and it turned out to be this guy. So, but the spin L function comes from more of this Langland's story.
So in this case, you have further just what you said. This question, right? F1 is equal to C times F2. Right?
Yes. So it's just, I mean, I am never. I cease to be surprised by this. Just knowing these few numbers which should not pin down a function really do. So what's really happening is something, all of these are local informations. The local information seems to be incomplete, but the fact that all of these local things are local parts of a global automorphic object makes them equal. So just local stuff being equal but not quite doesn't give you much. but the fact that it's automorphic, it's a very global concept, and that is way more powerful than we can imagine. So that gives us results of this kind. So it's a amazing situation. The reason I'm pausing here so much for questions is because now I want to shift gears a little bit, and I want to show you some current research and applications of all the concepts that we started so far. So my plan for rest of the lecture and tomorrow's lecture is to try to see what we know about Fourier coefficients and Hecke eigenvalues for Siegel modular forms. What kind of results that we have. For example, the first one that I'm going to focus on is if I have cusp form of genus n, Sk gamma n, and it's non-zero, then I obviously know when I write down the Fourier coefficients, some a of t is non-zero, right, by definition of the function being non-zero. But then I could ask a finer question, can I get a of t not equal to 0 where t is of some special form? Because maybe I want to do some application, some special form guys give you some other properties. So the question is that I look at the whole set of n by n symmetric positive definite half integral matrices. This is my indexing set for a of t, and I ask the question, is there a subset of this set such that given a non-zero cusp form, I can always have a Fourier coefficient non-zero out of this subset. In other words, all Fourier coefficients a of t equals 0 where t comes from the subset implies f is 0. So I want to see how far I can go and how many applications I can get out of each such step. So let us denote by Sn is set of n by n symmetric positive definite half integral matrices, and then the problem is what subset of Sn determines f in Sk gamma n. Okay, of course the whole Sn does, because if you knew all the Fourier coefficients, you of course know the function. So the first thing I want to do the basic one. If I have t, then I should at least be able to remove the GCD. So at least I want something a of t equal to not equal to 0 where the t has GCD 1. Okay, these are called as primitive matrices. So let us write down that set. So for t in Sn, content of t, this is defined by, so C of t is max a in n such that a inverse t is half integral. So this is a roundabout way of saying that your a is the GCD. If you have just m r by 2 n, but if it's n by n matrix, I don't want to get bothered by this. So basically you say t is primitive if content of t is equal to 1. And now my question is, if I give you a cusp form Sk gamma n such that a of t is equal to 0 for all t with content 1, does it necessarily mean that f has to be 0? This is indeed actually true, and it's a theorem of Zagier. So theorem of Zagier from 1981, which says that let f be in Sk gamma n such that a of t is equal to 0 for all t bigger than 0 such that content t is 1, then f is identically 0. By the way, let me tell you one thing, there are lots of such theorems or hypotheses that you can write down. If you add the hypothesis that f is a Hecke eigenform, things become much easier. If you don't assume Hecke eigenform, it's much harder problem, because as soon as you have a Hecke eigenform, you have the power of the L functions, and this is a very important tool that you can use. And you can see, just because you know such a theorem for Hecke eigenforms doesn't mean you can get it for a general form. So you take a general modular form, you know there is a basis of Hecke eigenforms, so write it as a linear combination. Well, but if a of t is equal to 0, it doesn't mean that the individual Hecke eigenforms also have the Fourier coefficient 0 at those guys. So I cannot, the Hecke eigenform result doesn't translate to a non-Hecke eigenform results ever. So there is no easy transition, and at the same time Hecke eigenforms assumption gives you extra tools. So the proof is easier and the transition is very hard. So there's only one non-trivial exciting exercise today. It's the proof of this one. Wait, Zagier is only for genus 2, okay? and he does not even assume cuspidal, he can take M. I should be careful with this thing. So, there are Zagier's theorem was only for genus 2. So, I have put this into an exercise, and the reason I did this is sneakily I have introduced Fourier Jacobi expansions in the exercise. So, Fourier Jacobi expansions, their Taylor expansion in the z variable, and really cool ideas, very simple ones, each one of them actually gives you a highly non-trivial result. So, please 11 to 3 look at that exercise, and all the steps are written down. So, it is not like prove this theorem. I mean, Zagier is like the smartest person alive or something, we can't expect to prove the theorem in 4 hours. Maybe Zagier did it in 4 hours, who knows, but not us, okay. But I have laid down the steps, so look at it, and I will be very excited to discuss this in the afternoon. So, this was 1981, and now from 1981 to 2009, so this is by Yamana. This was generalized to higher genus as well as level. So, maybe before we write down the theorem, I want to maybe write here. So, let n be a positive integer, Siegel congruence subgroup of genus n and level capital N. This is defined as gamma 0 of capital N. This is your usual genus 1. I am going to put a superscript here. This is A, B, C, D in gamma n such that C is congruent to 0 modulo n. So, the usual gamma naught n analog, but in higher genus. So, what Yamana did was actually prove it for such kind of guys. So, let f belong to m k gamma naught n such that A of t is equal to 0 for all t with content t dividing n, then f is identically 0. So, he had to he could not do it with just content t equals 1, that is not enough. You need content t equals 1 or any number which divides n. So, it is a bigger set, but the ideas of Yamana are very much similar to the proof of Zagier, but he just did it in higher dimension, and he did it actually in much more generality and so on. So, this is Yamana's result. Of course, if you do not want to assume this content dividing n, you do not want this big set, but you still want to just go back to your content 1 set, then you have to avoid some modular forms here. So, you have to avoid forms which are called as these old forms, which actually are secretly living on a smaller level, but pretend to be of level n. You avoid them. If they are genuinely in level n, then you can drop down to content 1. So, you can say that, okay, so S K O. Now, I have this craziest notation here, right. So, if without the O, these are just cusp forms on these guys. The O stands for old forms, okay. O is for old forms here, and these I am defining as f of dz, where f actually comes from something smaller, dm divides n, and m is not equal to n. So, strictly smaller guys. You take something of smaller level, and if you just multiply it with, you can multiply it with any d such that this thing happens, and you get another guy. So, these are what are called as old forms, and then if you avoid these old forms, then you can write down the theorem which says, so theorem is now Ibukiyama and Katsurada. You see, this is 5 years ago. We are now in the world of very recent mathematics. They say that if f is in sk gamma 0 n of n with Fourier coefficients a of t, suppose f lies in the orthogonal complement of the old forms. It is my fault that I introduced so much notation, I keep on forgetting what to write. Then A of t equals 0 for all t with content t equals 1 implies f is identically 0. So, they could bring it down to the subset of Sn being the primitive ones. So, this is like the best possible story for a problem right here, where the subset is the subset of primitive matrices. You have the full answer. Of course, you will tell me that we did not look at all Siegel cusp forms, only those with respect to these kind of congruent subgroups. So, indeed there are questions about other congruent subgroups open, and those can be addressed, but for these Siegel congruent subgroups of any level, this thing is answered and known. I know here I have been writing down results rather than telling you the proofs. Okay, we are going to look at the proof of this in the afternoon, but these guys I just wanted to tell you the current status. So, 2012, this is what we know. Now, these things are well and good. In fact, I should have, but I did not try to look up what applications that we get out of such a theorem, but there is a even smaller subset of primitive matrices which is extremely relevant for various applications. I am going to give you two applications of a theorem which is an even better theorem than this, in the sense that I take not just primitive matrices, but the matrices which I remember we call fundamental, such that not just that the GCD is 1, but the discriminant that you have, determinant 2t, is a fundamental discriminant. So, these are even smaller subset, and we want a theorem exactly of this kind for such set of Fourier coefficients as well, and that I have two applications which are amazing applications that come out by knowing something about these Fourier coefficients. So, let me write down what I mean by these fundamental matrices T. So, if you have T in S2, so I am now restricting to n equals 2, okay, from now to the end of the lecture today, it is all n equals 2, and the discriminant DISC of T is defined as minus 2 times determinant 2t. It is a negative number, and I say that T is fundamental if discriminant of T is a fundamental discriminant. And what do I mean by that? So, this fundamental discriminant means, so D is either congruent to 1 mod 4 and square free, or D equals 4m, m is congruent to 2 or 3 mod 4 and m is square free. So, if you have an integer, you check if one of these two conditions is satisfied, that is the definition of being a fundamental discriminant. It has a connection with discriminants of quadratic extensions, etc., and if you do not want to bother with it, this is all you have. Already you can see that if your matrix is fundamental, it has to be primitive, because if it was not primitive, there was some GCD, as soon as you take a determinant, the square of the GCD comes out, and these guys are square free and so on, right. So, fundamental T is primitive. So, I am indeed looking at the subset of what I had earlier, and then I want to write down the following theorem. This is a theorem due to Abhishek Saha, and this is, when did Abhishek do this? 2013. So, let k bigger than 2, n square free. If n is bigger than 1, then let k be even. If n is equal to 1, you do not care about the parity. So, let f be non-zero cusp form of weight k with respect to the Siegel congruent subgroup of level n, and suppose that this lies in the orthogonal complement of the old forms, then, well, you see, if you look at Zagier's theorem, it says that A of t is equal to 0 for all t implies f is equal to 0. So, f not equal to 0 means there exists one t, right. So, actually what Abhishek proved was, well, if f is not equal to 0, there exists infinitely many fundamental t's. So, he was able to show then there are infinitely many fundamental matrices T such that A of t is not equal to 0. In fact, he gives you quite a good estimate of if you look at all fundamental matrices T up to determinant x, he gives you an estimate how many Fourier coefficients are not 0 depending on x. I don't want to write down all that complicated stuff, but this is certainly what he is showing. So, the major ingredient of the proof of this theorem is actually an analogous statement about half integer weight modular forms. So, we have seen half integer weight modular forms a couple of times, and a half integer weight holomorphic modular form has its own Fourier coefficient C of n's, right. And what Abhishek proved using analytic number theory methods is that if you have an arbitrary half integral weight cusp form, then there are infinitely many fundamental discriminants d such that C of d, the Fourier coefficients of that guy are non-zero. So, that is where a lot of analytic number theory goes in. There are lots of results of this kind in literature in the area of analytic number theory, and he was able to do it for the square free level, that is right here. And then how does he relate it to these Siegel modular forms? It is a very neat trick. So, basically I do not want to write down the proof here, but you take such an f, you can see that such an f satisfies the hypothesis of Ibukiyama-Katsurada theorem. So, that guarantees a primitive t. Okay. So, primitive t prime such that A of t prime is not equal to 0. Okay. Now, t prime is like n r by 2 r by 2 m, okay. And these guys give you quadratic forms as n x squared plus r x y plus m y squared. And now, it is a simple theorem which says that if you have a primitive which means n, r and m have GCD 1, then this quadratic form you can find infinitely many x and y such that the value of the quadratic form is a prime number. So, this evaluates prime numbers. So, he says, well, since there are infinitely many prime numbers, pick one prime number which is away from n, does not divide n, and then you know that t prime evaluates this guy. So, you take the t prime and you do something like this and you get a 0, where G is an appropriate matrix in SL2Z. And you know Siegel modular forms, if you have a Fourier coefficient A of t, the value of A of t is the same as value of A G transpose t prime G. So, if the first one was non-zero, the second one was non-zero as well. And what this guy looks like is something here, something here, something here, p, or maybe I can write it as n, r by 2, r by 2 and p. So, he fixes on this p and he says, I am going to zoom in on a non-zero Fourier coefficient such that the lower right entry is a prime number p. And the reason why he is doing it is, if he would have been able to get a non-zero Fourier coefficient where the lower right entry is 1, it would have been immediate. Then you can quickly argue that you can find a fundamental 1. But the existence of non-zero Fourier coefficients of an arbitrary Siegel cusp form with the 1 in the lower right entry is an open conjecture. We do not know that, and it is a very important open conjecture in the sense that in the literature there are lots of theorems which starts with assume blah blah blah, hence blah blah blah. Okay. So, but you do not have it, but you can get a prime p, and then it does take this prime p, and from A of these guys he cooks up a half integral weight modular form. So, I do not want to write down the definition of Fourier coefficients etc. In the notes I have them explicitly, but I do not think it is going to be much of an advantage to write it down here. So, he cooks up this Fourier coefficient C of n's, he puts it together into a Fourier expansion, he is able to show it is a half integral weight modular form, and then its result on non-vanishing of Fourier coefficients of half integral weight modular forms gives you this thing. So, it is a very intricate web of ideas, and they build on lots of works of previous people and a completely disjoint world of analytic number theory. So, lots of things coming together giving you a theorem of this kind. And I will help you appreciate this even further, because I am going to give you two major applications which came out of this theorem here. One of them we will discuss today and the other one we will discuss next week.
So when you say half integral here, they are classical.
Yes, so you just summation Cn e to the 2 pi I n tau, where tau is in the complex upper half plane, and the C of n is kind of defined, C of say m is kind of defined out of some sum of a n r by 2 p with the n and r somehow depending on m. So, you just you define it as a finite sum, you just cook it up explicitly. So, there are I mean you cook up a Fourier expansion does not mean it is a modular form. So, you have to show that, but that is done, and getting these Fourier coefficients to be non-zero for fundamental, that is a completely different. So, that part of his paper I am not so familiar with, because even though the thing that I wrote down where I wrote a paper in analytic number theory, still my knowledge is not deep enough. Maybe I can appreciate it, but I certainly can't do it myself. Yeah, so this is Abhishek's theorem, and you can already see this is only for genus 2. Okay, genus, higher genus, you have absolutely no idea what's going on. So, before we look at the application that I am going to talk about today, I want to tell you about the thing that will happen next week. So, basically if you start with these Siegel modular forms, you are going to construct automorphic representations, etc. And then there is this important question of taking the Siegel modular form and a genus 1 modular form and looking at an L function of these guys together. So, it is a degree 4 times degree 2, so degree 8 L function. And we will spend quite some time next week on this degree 8 L functions. We will see that we want to show its nice analytic properties, or we want to show arithmetic properties. For example, you know that the Riemann zeta function evaluated at even integers is a rational number about pi to the 2k. So, these are the special value results. So, you might want to show such kind of results for these L functions as well. And as I have been telling you many times, the L function starting point is to write down an integral which evaluates the L function. So, this integral was obtained by Furusawa, but Furusawa made one assumption, that these Siegel modular forms have to have fundamental Fourier coefficients non-zero. If that is the case, then you would get what is called as a fundamental Bessel model. We will look at these Bessel models later, and those fundamental Bessel models give you an integral which gives you the L function. So, for about 2.5 decades, the whole theory was up to the assumption that Siegel modular forms have non-zero fundamental coefficients, and in 2013 then Abhishek did it and everything became unconditional. So, this is was a very important result. I mean, me and Ralph and Abhishek have written 4 or 5 papers on this topic, and we are very grateful to Abhishek, because otherwise everything would have been conditional on something which we do not know is going to be true or not, but it is indeed true. So, that will come up later. But today what I want to tell you is this thing already gives you something quite interesting. So, an application. So, let us see, we want to do the following. Let us start with K, an imaginary quadratic field, okay, and this K has some class group. So, we were discussing something about class number 1, which tells us that every ideal is principal, but in general in number fields the ideals may not be principal, and that deviation from being principal is measured by this class group. So, it is a finite group, and take a character lambda, character of the class group. Okay. Now, out of this quadratic extension and this character, you can cook up a weight 1 holomorphic modular form of genus 1. And the way you do it is I am going to just write down the Fourier expansion. You can define Z is in H1, and this is defined as you take all non-zero ideals in the ring of integers. You take, so the lambda is a character of the class group. So, class group contains ideals. You can evaluate the character at the ideal, and you do e to the 2 pi I norm of the ideal times Z. So, it turns out that this guy is a weight 1 modular form with respect to gamma 0 of D. And what is this D? So, this has fundamental discriminant minus D. It is an imaginary quadratic, so it is a negative number, and you also have a character, you get the Kronecker symbol here. Okay, so, this is a weight 1 modular form, and you get cuspidal if and only if lambda is not plus minus 1, which is not so important. And now the question is the following. Question is, given f in sk gamma naught sk1 gamma naught n1 and g in sk2 gamma naught n2, can we find k and lambda such that the L value at 1/2. So, if this product is non-zero, they have to be simultaneously non-zero. So, the question is, given arbitrary f and g, can you actually come up with a choice such that the central value of these L functions, so this is a GL2 cross GL2, if this is Fourier coefficients an, this is Fourier coefficients bn, this is essentially the Dirichlet series an bn over n to the s. So, if you have not seen this thing, it is just that guy. You are sitting here, so I should not have to tell you the importance of the half. Okay? The half is the central, the Riemann hypothesis and $1 million and everything. So, you really want to know what is happening, whether it is non-vanishing at half or not. And so, the question is, given two arbitrary guys, can you find k and a lambda such that you get simultaneous non-vanishing? So, this is in general an open question. Okay? This is a is a very complicated question. There is a different version that you might have seen. So, these are giving you weight 1 modular forms. So, this is a GL2 cross GL2. Instead, you could just put a character here, right? Twist f by a character means if you have summation a n e to the 2 pi I n z, change the a n by chi of n a of n. So, just multiply by a character. You could ask this question as well, given f and g, can you come up with a character chi such that L 1/2 f cross chi is non-zero and L 1/2 g cross chi is also non-zero. Those are smaller L function. I think that is even harder. Okay, so, it is kind of counterintuitive, but it is even harder. But I have a result for this one. So, that is the reason I am writing this down. And as I said, for general f and g, we have no idea. But I am going to choose some specific conditions on the k1, k2, n1, n2. The reason is, as soon as I do that, I will be able to construct some Siegel cusp form which satisfies this kind of stuff, and then the non-vanishing of Fourier coefficient is going to be related to non-vanishing of L function. So, Abhishek's theorem has the application of this guy because these things give you a Siegel cusp form, and somebody else showed already that Fourier coefficient non-zero of that cusp form gives you non-vanishing of these L values. So, this theorem of getting non-zero Fourier coefficients has an amazing application to a completely different world. Let us see what is going on, and we already probably heard the name of the Siegel modular form. These are the Yoshida lifts. So, what do we have? So, in general, very hard problem, and so maybe let us specify something a little easier. So, let us take n1 and n2 to be square free. His theorem is only for square free, so let us not mess with this. Also, a slightly strange condition, but we want GCD of n1 and n2 to be bigger than 1. Usually you take it co-prime, but you want them to have common factors. And let us set n equals the LCM. So, what I want to do, these are my n1, n2s, and I want to make the choice of k. So, let f be in gamma 0 n1, but I want to take just weight 2, not arbitrary thing here, and g in s gamma 0 n2, and here I allow any even weight. Okay, here I don't put any restriction, any even weight is okay, and I want them both to be Hecke eigenforms. So what do I mean by Hecke eigenforms? When I look at primes which do not divide n1 and n2, there are Hecke operators and eigenvalues, etc. For primes dividing n1 and n2, there are these things called as Atkin-Lehner operators. So you say that they are also eigenfunctions with those, and in fact they have some common factors, right? N1 and n2 have some common factors. So we also assume such that Atkin-Lehner eigenvalue for p dividing n1 and n2 are equal. Okay, so these are my f and g's, and then a classical construction due to Yoshida tells us the existence of the following Siegel modular form. So there exists non-zero f in Sk plus 1. So the level n is now the LCM, the weight is k plus 1, so you have 2 plus 2k, the half of that, such that number 1, f is in the orthogonal complement of the old forms. Number 2, it's a f is a Hecke eigenform. Number 3, this is the thing which gives you this L function property. How should I write this? Ls f cross sigma is Ls little f cross sigma times Ls g sigma for all sigma cuspidal automorphic representations of GLMA for all m. So whatever crap you want to throw in, it's fine. If you take the cross here, it factors. So this is another. So if you did not put anything, if sigma was just nothing, Ls, the spin L function, is the product of these two L functions. But if you want to cross it, because I want to cross, right, at some point I want to cross, and so if I cross, still factors. So these guys are called as Yoshida lifts. Yoshida studied them first in a paper with Ralph, Abhishek, generalized Yoshida's constructions for much more general setting, but this is Yoshida's lift. Okay, so you see,
Do you want to assume f and g are new or something like that?
Hecke eigenform, oh yeah, you're right. So new forms, yes, because you don't want them to be old forms. Again, so it's just like we are avoiding the old forms here, we want to avoid the old forms here as well. Thank you. New forms. So of course, you can see I unfortunately just erased Abhishek's theorem, but these modular forms are exactly satisfying hypothesis of Abhishek's theorem, right? Which basically tells us that for this f, Saha's theorem implies that there exists infinitely many fundamental t such that a of t is not equal to 0. In fact, in his paper he shows a little more. He shows that not just a of t, but some kind of a weighted sum of these guys also works. So if you take these k and lambda as before, let us define Fourier coefficient of this kind. So this is summation lambda of c a of c for c in the class group inverse. So of course, if you are in the class group, the lambda is a character of the class group, so lambda of c makes sense. What does a of c mean? I mean, these are ideals, but if you have any ideal in the class group, you can have a one-to-one correspondence with quadratic forms. As soon as you have a quadratic form, there is a one-to-one correspondence with your 2 by 2 matrices T. So that C is corresponding to that T. And why did I just say C? Because if you chose some other representative of the class group, it's the same as doing G transpose TG. And I know that my Fourier coefficients don't change with that. So in fact, what Abhishek showed that there are infinitely many k and lambda as before, so that this guy is not equal to 0. So, just the Fourier coefficient not being able to 0 does not mean that this guy is non-zero, because you might add up something and get 0, but indeed this is not equal to 0. And this was the main thing that he showed, because now there is a theorem due to Dipendra Prasad and Ramin Taklu-Bikash, which says that R f k lambda not equal to 0 implies this product is not equal to 0 in the case of Yoshida lifts. So, let us say this way: Prasad and Taklu-Bikash showed that R f k lambda not equal to 0 implies L 1/2 f cross theta lambda not equal to 0 for f a Yoshida lift. So, that theorem is about Siegel modular forms, nothing to do with these guys here, but if you have a Yoshida lift, then they are able to show such kind of a condition. And now putting together this thing here and this thing here and all of that, we get that actually if you have little f which is weight 2 and little g which is weight 2k, then there are infinitely many k and lambda, such that there is simultaneous non-vanishing. So, this is a big ingredient which is a kind of black box as far as Abhishek Saha's result goes, but as long as you have something like that, all the construction and the key point being non-vanishing of fundamental Fourier coefficients actually gives you simultaneous non-vanishing of central L values. So, yeah, I have painted a big picture here with lots of complicated stuff, but they all add up to highly non-trivial results. So, this is the kind of thing I wanted to give you a glimpse of. So, what I would like to tell you is that it is fine if there are things that are unknown and strange, you can't understand them right away. The point is just to see the connection between the basic objects that we were discussing, L functions that we talked about, and their Fourier coefficients that we have studied for so long. The properties of non-vanishing connect to lots of different things in the world and give you highly non-trivial results, which you have no way, so far there is no other way of getting results of this kind. I want to mention just one last thing. So, Prasad and Taklu-Bikash, they proved this in this case. Result of this kind for all cuspidal Siegel modular forms is a open problem. In fact, what is an open problem is, it is not just one way, it is if and only if. The Fourier coefficients, non-vanishing completely determines the non-vanishing of the central L value, and I know many of you are just starting out with your PhD and your research life. Central L values is a very, very important subject. Okay? If you are not being told this so far, this is the first time, then you should underline it and say this is a very important thing. So, such kind of criteria for non-vanishing of central L values, these are very important things. So, in fact, in the simplest setting of Siegel modular form of genus 2 with respect to gamma 2, Bocherer gave a very precise conjecture. He not only said that this non-zero if and only if this is non-zero, he predicted a formula relating this guy to this guy, and that is called as Bocherer's conjecture. And yeah, so maybe I can write down what was Bocherer's conjecture, and that will be a good place to stop. So, f in Sk gamma 2 and k equals q square root of d with d negative and fundamental, then R f k absolute value squared, I am taking lambda equals 1. So, lambda is 1. Bocherer conjectured that there is a constant f, C f which depends only on f, such that these are number of roots of unity, the discriminant to the power k minus 1 L 1/2 f cross chi d, and this is the quadratic character corresponding to the field of extension. And this was Bocherer's conjecture. He made the conjecture in the 80s. This was proven last month. Okay? So, this is like current breaking news. Furusawa and Morimoto were able to get this result just last month. There is a much more general version with the lambda put in there, and that is not known. So, they could do only lambda equals 1 case. There is a formula relating r f k lambda absolute value squared to the central L value as well. And those of you who have seen this thing a little bit, I will try to connect you to something that you might know. So, this square of Fourier coefficient equals central L value was first proven by Walsh-Perget. If you have a half integral weight modular form G, which corresponds to an integral weight modular form F, then Walsh-Perget proved that if you take C of D, where D is a fundamental discriminant, absolute value squared, there is a formula relating it to L 1/2 little f cross chi D. So, capital F is replaced by modular form on gamma 1. This complicated thing is replaced by square of Fourier coefficient of the half integral weight guy corresponding to it. So, that was known by Walsh-Perget, that was first proven by Walsh-Perget, then Kohonen also did things. Recently Baruch and Moshe did it for mass forms, I did it in my thesis, but this is a higher genus version. So, this was a conjecture for 25 years, and last year I was at a conference and I was talking to Bocherer, and he was saying, oh, I am hearing that Furusawa and Morimoto have some results towards this, do you know something? I said, no, I don't. And then he was saying, you know, I am very happy that my conjecture has gotten so much publicity and importance during the last decades. I only hope that when it is solved, I will understand the answer. And Bocherer is very smart, but I don't know. What's being used by Furusawa and Morimoto is, well, let us see. I'm sure Bocherer will understand it. Yeah. So, let us stop here. Today we saw a very nice spectrum of very current non-trivial research connecting to what we learned in the first 3 lectures. Okay? So, we will continue discussing exercises in the afternoon.